All right. In this video, we will be going over section 4.5. Section 4.5 is about fundamental theorem of calculus. Okay, this is one of the most important sections in this course, Calculus 2. All right. I want to straight away start with the fundamental theorem of calculus, theorem 4.24. Let's see what the theorem tells us. Okay. If f is continuous on a comma b closed interval and uppercase f is any antiderivative of the lowercase f, then the definite integral of f of x from a to b is given by uppercase f of b minus uppercase f of a. Okay, this tells you a way to calculate a definite integral. Okay, if you know this function uppercase f, which is an antiderivative of your lowercase f, then you can find this definite integral by evaluating this difference. Okay, f of b minus f of a. As you can see, this makes our life much easier to calculate definite integrals. How did we calculate definite integrals in the previous sections? We use Riemann sums, right? We used Riemann sums and then we found the limit as n approaches to infinity. That was a very time-consuming procedure. But this gives you the definite integral very easily through this formula. Okay, the definite integral of f of x is equal to definite integral of f of x from a to b is equal to uppercase f of b minus uppercase f of a, as long as uppercase f is an antiderivative of your lowercase f. Okay, this is a very useful formula. All right, next we have this definition, evaluation notation. Okay, for any function uppercase f on an interval a comma b, the difference f of b minus f of a will be called the evaluation of f of x on a comma b and will be denoted by, you write f of x and then you put a square bracket like this and then you put the lower limit and the upper limit. What this quantity means is that f of b minus f of a. Okay, so this is a notation for f of b minus f of a. Whenever you see an expression like this, that means f of b minus f of a. For example, if you think about this, 2x squared plus 1, and then let's say 1 to 2. Lower limit is 1, the upper limit is 2. This looks like your a, this looks like your b, and this looks like your uppercase f of x. This is equal to 2 times, you plug in 2 in your uppercase f of x, which is in fact this function in this case, 2 squared plus 1 minus, and then you plug in the lower limit, that is 1. 2 times 1 squared plus 1. And then you simplify this expression to get the answer. All right, that's about evaluation notation. Let's move on. Next, I want to go over this theorem, theorem 4.26, fundamental theorem of calculus in evaluation notation. Okay, here is what the theorem tells you. If f is continuous on the closed interval a comma b, then the definite integral of f of x from a to b is equal to the family of antiderivatives. You evaluate the family of antiderivatives. Okay, here this notation is for the family of antiderivatives from the last section. Okay, what you do is you take the family of antiderivatives and put the limits. This is in the evaluation notation, and the evaluation notation is defined over here. Okay. By the way, here when you take this family of antiderivatives, it looks like this, right? Typically, a family of antiderivatives looks like this, where this f of x is an antiderivative of f of x, this lowercase f of x. Okay, then f of x, uppercase f of x plus c would be a family of antiderivatives. You can plug in this family of antiderivatives here and then evaluate that family of antiderivatives from a to b. When you plug in this family of antiderivatives, when you write the evaluation notation, you don't really have to put this constant c. You can just plug in uppercase f of c here. You don't really have to put this constant c. Why is that? Let's see. Okay, let's see what happens if I plug in just uppercase f of x for this expression. If I do that, you get f of x a to b. By definition, this is f of b minus f of a. Now let's see what happens if I plug in this whole thing here, the family of antiderivatives here. Okay, then f of x plus c, you have the evaluation notation a to b. By definition, you have f of b plus c minus f of a plus c. You just have to plug in the upper limit here and then minus you plug in the lower limit here. Lower limit is a. Okay. Now, as you can see, if you simplify this expression, you get nothing but f of b minus f of a. That means to find this evaluation notation, you don't really have to put the family of antiderivatives here. You can just put one antiderivative. Namely, you can just put f of x here. Okay. Even if you put the family of antiderivatives, you get the same answer. You get the same answer as the answer that you get when you put a single antiderivative f of x. All right, that's one thing that I want to remark, and that we will be using in today's lesson. Okay, next I want to go over this particular theorem, the net change theorem. Okay. If f is differentiable on a comma b closed interval, then the definite integral of f prime of x dx, f prime of x from a to b is equal to f of b minus f of a. Okay. Or in other words, what this theorem tells you is that f of b minus f of a is equal to the signed area between the graph of f prime of x and the x-axis on that given interval a comma b. Okay. If you want to find this difference, all what you need to do is find the signed area between the graph of f prime of x and the x-axis on that interval a comma b. All right, let's move on. Now I want to work on some examples. Here is the first example that I want to go over. Suppose a car traveled 100 miles along a straight path in 2 hours. If S of t describes the car's position in feet after t hours, and v of t is equal to s prime of t describes its velocity in miles per hour after t hours, find the signed area between the graph of v of t and the t-axis from t is equal to 0 to t is equal to 2. How do you find the signed area between the graph of s of v of t and the x-axis on that interval? Well, let's make it clear. We need to find the signed area between v of t and the t-axis. That means we need to find the definite integral from 0 to 2 v of t dt. That is the signed area between v of t and the x-axis in this interval 0 to 2, because the interval is 0 to 2. Okay, so this is what we need to find. This is nothing but definite integral of s prime of t from 0 to 2 dt. Okay, because your s prime of t is same as v of t, it's given to us. V of t is denoted by s prime of t is denoted by v of t. Okay, so this is what we need to find. Okay, again we are asked to find the signed area between v of t and the t-axis in this interval 0 to 2. That means the definite integral of v of t from 0 to 2. That's what we want to find. That means we need to find this. Can we find this? Well, by the previous theorem, by the net change theorem, we know that the definite integral from a to b f prime of x dx is equal to f of b minus f of a. So by the net change theorem, we see that this is equal to s of 2 minus s of 0, because you have s prime of t here, right? If you compare with this formula, if you have f prime of x here, you should have f of b minus f of a. Here you should have s of 2 minus s of 0, because this is your b, this is your a. Okay, so we have that. Now the question is, can we find this? Do we know this? First of all, what is s? S is the position. S describes the car's position. Your car starts at here, and let's say it's traveling in this positive direction. After time t, the car's position is s of t. S of t is the position. Okay, we know that this is the situation where t is equal to 0, and this is when t is equal to 2 hours. That's the interval of interest. You are interested in when in this interval t is equal to, from t is equal to 0 to t is equal to 2. Okay, at t is equal to 0, clearly s of 0 is 0, because your position is 0, you are here. Okay, you start measuring the position from here. And what is s of 2? After 2 hours, your position is whatever the distance you have here. What is the distance? It is given, it is 100. Okay, after 2 hours, you have traveled 100 miles. So that means s of 2 is 100. So we know both quantities. I know s of 0 and I know s of 2. I can plug them in here. This is equal to 100 minus 0, which is 100. Okay, that is the signed area between the graph of v of t and the x-axis on the interval 0, 2. Okay. Okay, that completes that example. Let's move on. All right, let's go over our next example. Use fundamental theorem of calculus to calculate the exact values of the following definite integrals. Okay, let's work on the first part, part A. How do you find this definite integral? Definite integral from 2 to 4 x squared plus 1 dx. Well, I can find the definite integral, this definite integral, if I can find an antiderivative of this function. Okay, can I find an antiderivative of this function? Because my goal is to apply the fundamental theorem of calculus. Okay, remember, again, this is the fundamental theorem of calculus. Okay, the definite integral of f of x from a to b is equal to f of b minus f of a, where uppercase f is any antiderivative of f of x. All I have to do is I need to find an antiderivative of lowercase f of x. Okay, if I have an antiderivative, then I can immediately find the definite integral given by this expression. Okay, so let me copy this theorem to that slide. All right, I have put down the theorem here, fundamental theorem of calculus. So to find this particular definite integral, I need to find an antiderivative of this function. What is an antiderivative of this function? To find an antiderivative of this function, you can use the formulas that we used, that we learned in the last section. Okay, so you can find the indefinite integral of this function and take one of those antiderivatives. Okay, so what is the indefinite integral of this function? We have formulas, right? So the indefinite integral of the first function x squared is x to the power 3 divided by 3. I'm using this formula, okay, to find an antiderivative. That would be, if you have x to the power k, an indefinite integral of x to the power k is 1 over k plus 1 times x to the power k plus 1. That is an antiderivative of x to the power k. Okay, so this is an antiderivative of x to the power 2. And then what is an antiderivative of x 1? That is just x. Okay, as you can see, This expression is an antiderivative of this function. If you differentiate this function, you get this function. That means by fundamental theorem of calculus, you can evaluate this antiderivative from 2 to 4 to find this definite integral. Okay. All right. Now let's evaluate this. This is equal to 4 cubed over 3 plus 4 minus 2 cubed over 3 plus 2. Okay. And if you simplify this, you will get 62 over 3. All right, let's move on to the next part, part B. We need to calculate this definite integral, minus pi to pi sine x dx. Okay, to calculate this, all what we need to do is we need to find an antiderivative of sine x. We know that the definite integral of sine x is minus cosine x plus c. So this is an antiderivative of sine x. Okay, minus cosine x is an antiderivative of sine x. So by the fundamental theorem of calculus, this definite integral is equal to minus cosine x. You need to evaluate that between minus pi over 2, minus pi and pi. You just put the limit, lower limit and the upper limit. Okay. Notice that this is an antiderivative of this given function. Once you have an antiderivative, to find this definite integral, all what you do is you plug in the limits for this antiderivative. Okay. You get the evaluation notation. So this is equal to, by definition, minus cosine, you plug in the upper limit, pi, and then minus cosine minus pi. You plug in the lower limit. Okay, if you simplify this, you should get 0. All right, that completes that example. Let's move on to the next example. Find the sine area between the graph of f of x is equal to 3 times e to the power 2x minus 5 minus 3, and the x-axis from x is equal to 1 to 3. Okay, use a graph to verify that the sign of your answer is reasonable. Okay, let's deal with that later. First, let's try to find the signed area between the graph of f of x and the x-axis. Okay, the signed area is given by, we know that from the previous sections, area is given by the definite integral of f of x from 1 to 3. So f of x is 3 times e to the power 2x minus 5 minus 3. To find the sine area between the graph of f of x and the x-axis, you need to find this definite integral. How can you find this definite integral? Well, you need to find an antiderivative of this function, right? To find this definite integral, we can apply the fundamental theorem of calculus. Okay, here is the fundamental theorem of calculus. If uppercase f is any antiderivative of f of x, lowercase f, then the definite integral of lowercase f of x from a to b is a uppercase f of b minus uppercase f of a. Okay, all what you need to do is to find an antiderivative of your lowercase f of x. So that means you need to find an antiderivative of this function. Again, here we are going to need some imagination. So if you try a function like this, uppercase f of x is equal to 2 over 3 times e to the power 2x minus 5 minus 3x. I put minus 3x here because when I take the derivative of this function, I should get minus 3, right? Now, if I take the derivative of this piece, I get minus 3. That's what I want here. Okay. And if I take the derivative of this part, I get this function. That's what I want. Okay. So if I take the derivative of this whole thing, you will exactly get this function. By the way, here it should be 3/2, okay? Not 2/3. This should be 3/2. Now, if you take the derivative of this function, you are going to get this function. That means this is an antiderivative of this function. Now we are ready to apply the fundamental theorem of calculus. By fundamental theorem of calculus, fundamental theorem of calculus, I will write FTC for the fundamental theorem of calculus, okay? We have the definite integral of f of x from 1 to 3 is equal to this expression in the evaluation notation. Okay, remember that should be equal to f of b minus f of a, right? That is nothing but f of x in the evaluation notation. A to b, okay? This is the evaluation notation for this expression. All right, so but this f of x is nothing but your antiderivative. So your antiderivative is this one. So let me put that in here. 3/2 times e to the power 2x minus 5 minus 3x. Put the evaluation notation 1 to 3. Now, if you plug in these numbers, you will get 3/2 times e to the power 1 minus 9 minus, this is your f of b. I just plugged in 3 in this function, and then minus f of a. That is 3/2. You plug in x is equal to 1 now. E to the power minus 3 minus 3. All right. Now, if you calculate this using a calculator, you will get minus 1.997. Okay, roughly you will get minus 1.997. All right, that is the signed area. Okay, signed area between the graph of f of x, which is this function, and the x-axis on that interval 1, 3. Okay, so that's the signed area, and then we are asked to use a graph to verify that the sign of your answer is reasonable. Sign of my answer is negative here. Okay, now we need to use a graph to verify that. Here is the graph of f of x in that interval 1 to 3. Okay, as you can see, the area below the x-axis is bigger than the area above the x-axis. That's clear from this picture. Remember, area below the x-axis is counted as a negative area, and area above the x-axis is counted as a positive area when you take the signed area. Okay, that's why this is negative, because the area below the x-axis is bigger. Okay, so the sign is reasonable. Okay, we may write a statement like sign is reasonable. Sign means the negative sign is reasonable since the area below the x-axis is bigger than the area above the x-axis. Okay, that's the reason for your sign to be negative. All right, let's move on. Suppose f is a function whose derivative f prime is shown next, right here. Graph of f prime of x is given here. Given that f of 1 is equal to 3, use the fundamental theorem of calculus and the graph of f prime to approximate f of 4. Okay, how do you use the fundamental theorem of calculus and the graph of f prime of x, which is given here, to approximate f of 4? Let me focus on this particular integral. Definite integral of f prime of x from 1 to 4 dx. Okay, Notice that f of x is an antiderivative of this function f prime of x. Okay, clearly f of x is an antiderivative of f prime of x. Of f prime of x. That's clear, because if you take the derivative of this function, this is what you get. So now by the fundamental theorem of calculus, you have, I will write f t c, fundamental theorem of calculus. By fundamental theorem of calculus, we have this is equal to f of 4 minus f of 1. Because f of x is an antiderivative of this function. Okay, this should be equal to f of 4 minus f of 1. I know my f of 1, it is given to me 3. If I can find this value somehow, then I can find f of 4. Okay, that's the idea. Somehow we need to find a way to find this definite integral, approximate this definite integral. Okay, how do I find what is this definite integral is about? The graph of f prime of x is given to us on the interval 1, 4. The definite integral of f prime of x from 1 to 4 is nothing but the area under the graph of f prime of x and the x-axis. That means the definite integral, this definite integral is the area under the curve f prime of x. Okay, so that means this definite integral is equal to the area under this curve. So you need to find this area. How do you find this area? Well, to find that area, notice that area of a one box, one of these small boxes, area of a one of these small boxes is 1/4. Would you agree with me? That is because this length is 1/2. This length is also 1/2. 1/2 times 1/2, which is 1/4. Now what you do is you count the number of boxes in this area. Okay, 1, 2, 3, 4, 5, 6, so on and so forth. And of course, here you have half a box here. And you may take this piece as 1/8 of a box, and so on and so forth. You just need an approximation. Okay, you will see that you have 26.5 boxes. Altogether, there are 26.5 boxes. Okay, here altogether there are 26.5 boxes. That means what is the area of that shaded region? Area of the shaded region is equal to 26.5 times 1/4, because you know that area of a one box is 1/4, and altogether you have 26.5 boxes. If you multiply these two together, you will get an approximation for your area. Okay, so this will be roughly 6.6. So the area is known. That area is nothing but this definite integral. Of course, that's not the exact value, but this would be an approximation for this definite integral, because this definite integral is the exact area under this curve on the interval 1, 4. So that means this is equal to 6.6. Let me put that there. 6.6 is equal to f of 4 minus f of 1 is 3, which is given to us. That will give you f of 4 is equal to 9.6. Okay, that gives you the value of f of 4 approximately. All right, let's move to the next example. Here is the next example that I want to go over. A termite colony is slowly dying off in such a way that the number of termites P of t after t weeks is changing at a rate of P prime of t is equal to minus 567.68 times 0.794 to the power t. Determine the number of termites that die in the first 3 weeks and interpret your answer as an area under a curve. Okay, how do you determine the number of termites died in the first 3 weeks? Well, let's say what is the expression for the number of termites? We know that P of t is the number of termites. Okay. Then P of 0 is the initial number of termites. Okay, P of 0 is the initial number of termites. Okay, P of 0 is the initial number of termites, and P of 3 is the number of termites after 3 weeks. Okay, all right. Now, what are we asked to find? We are asked to find the number of termites that died in the first 3 weeks. That means we want to find P of 0 minus P of 3. We know that this colony is dying out, then P of 0 has to be greater, right? And P of 3 should be a number less than P of 0. And to get the number of termites that died in the first 3 weeks, you need to subtract P of 3 from P of 0. That will give you the number of termites that died during the first 3 weeks. So this is our target. This is what we want to find. Okay. To find this, we are going to use the net chain theorem again. By net chain theorem, we know that we have definite integral from 0 to 3 P prime of t dt is equal to P of 3 minus P of 0. Okay. Now, what I'm going to do is I'm going to compute this. This is given. P prime of t is given. It is this one, this expression. Okay. So let me plug that in here. 0 to 3 minus 576.68 times 0.794 to the power t dt is equal to P of 3 minus P of 0. Okay. Here is the equation. As you can see, this is a constant. I can pull this constant out. Minus 576.68 times integration from 0 to 3, 0.794 to the power t dt is equal to P of 3 minus P of 0. Okay. Now we need to find this definite integral. We can use the fundamental theorem of calculus to find this definite integral. All what you need to do is you need to find an antiderivative of this function. Of course, we know how to find an antiderivative of these types of functions. If you go to the previous section, theorem 4.17, the indefinite integral of b to the power x is equal to 1 over ln b times b to the power x plus c. That means this is an antiderivative. Okay, so this is a formula for the antiderivative, for an antiderivative of b to the power x. Okay, so this is the antiderivative. So we can find an antiderivative using that formula. That will be minus 576.68. You have to take the evaluation notation 0 to 3. An antiderivative of this function would be 0.794 to the power t divided by ln 0.794. Okay, this is an antiderivative of this function. Then by fundamental theorem of calculus, you take the evaluation notation of this antiderivative. Okay, you put 0 here and 3 here. All right, now if you evaluate this, you should get your answer to be minus 1205 248.58. That's what you get. Okay. Remember, I calculated this is equal to, this number is equal to P3 minus P0, P0. P3 minus P0 is equal to minus 1248.58. That means if you multiply this entire equation by a negative sign, you get P of 0 minus P of 3 is equal to plus 1248.58. Why did I multiply this equation by 0? Because I need P of 0 minus P of 3. Okay, that's what I wanted. I wanted P of 0 minus P of 3. That is the number of termites died during the first 3 weeks. So this many termites died during the first 3 weeks. Since the number of termites has to be a whole number, we may write 1249 termites died. During the first 3 weeks. Okay. All right. With that, we conclude section 4.5. I'll stop there and I'll see you next time.